Hi, in this video I'll be presenting Gauss's law in less than 12 minutes, and hopefully at the end of it you'll find it easier to understand the law. Before getting into the law itself, it would be worthwhile to take a look at basic terms like net flux and electric field. Gauss's law is all about electrostatics. It's not connected with current flowing through circuits. So create a sheet of charge, which is the red one here. Give it a positive charge. It distributes all over the face, on the front and on the other side, and the flux lines emanate from it. Looking at this image, the flux lines are the yellow colored arrows that you see here. There is a pink dot there where we will later on find the electric field strength. The electric field strength E is something like a pressure. So if you multiply E into the frontal area that's in front of that arrow, you will get the flux. So that's the connection there between flux and E. When you put a closed surface, here it's a kind of green colored block, you have an area at the end which is in blue color. That's the frontal area, and that frontal area is perpendicular to the direction of the flux lines. Let's take a small problem. So the electric field strength is given as 200 newtons per coulomb, is acting from left to right, and we have to find the flux. So the flux is simply the multiplication of E into the area. So plug in the value of E, 200 newtons per coulomb, multiplied by the area of the sheet that the person has put in the way of the flux lines, and you get the value of the flux. So if we were to theoretically find out the field strength at a point P, which is that dot on the screen there, we artificially plug in an imaginary closed surface which is again perpendicular to the field lines and coincidental with that point P. So in this case we have plugged in a cylinder, an imaginary cylinder. So the flux lines come out through the end of that cylinder on the right side. That round face that you see there, they also come out on the other end of the cylinder, the round face that's behind the red sheet. So in this way you have two perpendicular areas through which the flux lines come out. The question is, do the flux lines cut the round part of that cylinder? And the answer is no. The flux lines are parallel to the round cylindrical surface of that cylinder, and there is no flux coming out of those round cylindrical surface. It's only the perpendicular areas which are important. So coming to Gauss's law, you can see the flux is E into dA, and Gauss's law just equates the flux with the charge inside the closed surface. In our example, it could be the charge inside the cylinder or the charge inside the rectangular block that you saw in those images. So there are only a couple of things to be done to understand Gauss's law: the flux on the left hand side and the charge by epsilon 0 on the right hand side. The integral symbols are to be explained later on in this video. Coming back to that sheet of charge, the area of that cylinder on the right side and on the back side was each dA. You add them and you get 2 dA. So the flux is E into 2 times dA. dA is a small area, infinitesimally small area. So equate that with Q by epsilon 0. In this, a new term has been introduced called sigma, the charge density. So the charge density is charge per unit area. This has been done here just to cancel the effect of dA. So if you put charge density into dA into the equation, the dA cancels on both sides and you get E is equal to sigma by 2 epsilon 0. That's a very neat little equation. However, you see that there is no distance x in this equation. So we use Gauss law for a sheet. We found the flux, we found the charge, and we matched them both. And as you can see on the notes below, for a particular sheet for a uniform electric field, the distance of the point P from the sheet is not entering into the equation. Let's now take a look at whether we need to plug in a cylinder always. Not really. So in the image we have plugged in a rectangular block, and once again you will have a dA on the right side and a dA on the left side, and the derivation will be the same. Let's take a look at a charged sphere. We are moving around the sphere. Take a look at it. The sphere is not rotating, and the first thing to notice is that the lines of flux are coming out radially. All the charge is accumulated on the surface of the sphere, and the arrows emanate from there. A closer look at the sphere, and you can see small blue patches. These are infinitesimally small areas. Each one of them is dA. So when you integrate, as per Gauss's law, integration of all these little blue patches, you get the sum integral of individual E into dAs, E in 1 dA1, E2 dA2, and so on. And in every case, the flux line is perpendicular to that blue patch because it's a sphere. So once again, you find the flux, which is E into dA. In the case of a sphere, the total surface area of the sphere integrated will be equal to 4 pi r squared. You find the charge, just Q, you match them up, and you can easily derive the equation for the electric field strength. So this is just a simple three-step approach of finding the flux, finding the charge, and matching them up. We will now look at areas that are not perpendicular. Suppose someone tilts that block in the lines of the flux. You can see that the green colored block is not really perpendicular to the flux lines. The frontal area in this case has to be found. So how do we find that? So if we take a simple plane, you have to drop a normal to that surface, which is here the pink arrow, and the one beside it shows that the orange colored area is the frontal area. It's a projected area of that green one in the direction of the flow of flux. If we take a top view of that same thing, you can see that the green area is tilted, the pink normal is perpendicular to that. There is an angle, say angle B, between that area and the direction of flux lines. The white arrow is the resolving of that normal along the direction of the flux lines, so that's cos theta. If you would draw a right angle triangle there between the pink arrow, the white arrow, the pink arrow acts as the hypotenuse and the white arrow is the base of that triangle, so therefore that is cos theta. If the pink arrow represents dA, then the white arrow is dA cos B. Could be cos theta or whatever we call that angle. This helps to calculate the flux through any tilted surface, no matter what angle it is. So let's look at a problem to get our numbers better. So there is a problem where E is defined as y into radius. So y and the radius is already given in the problem. It's a sphere. So for a sphere, we have to plug in the surface area as 4 pi r squared. All the flux lines are radial. So find the flux, which is E to 4 pi r squared. Find the charge, which is q by epsilon 0. So just plug it into the equation and you get the value of q. So in conclusion, we did something very simple. We found the flux, we found the charge, and we just matched them. So if you follow this route, you will not have a problem in understanding Gauss's law, and you will be able to solve a number of problems. I hope that this video was fairly easy and interesting to understand. Thank you, and have a great day. Bye-bye.